Let's practice solving an application word problem together dealing with quadratic equations where we're looking for some missing integers. For this particular problem, we are looking for two positive even consecutive integers. Now, it's important to know that when we are making up variables to represent an even number, we can't just use x because x could be even or it could be odd. So let's talk real quick about how we can write a mathematical expression that guarantees an even number. So we're looking for two consecutive even integers, so they have to be next to each other. Now, to write an expression, we can't just use something like x or n, which is the variable I'm going to use here, but instead we're going to go ahead and write the expression 2n. Now, n could be anything in the world that's an integer, and if you multiply it by 2, it's always going to result in an even integer. That being said, for our second even integer, that's actually going to have to be the expression of 2n plus 2. Or we could go ahead and say it would be the expression of 2n minus 2. Let's talk about why this is the case real quick. So let's talk about a couple quick examples. Let's look and say, let's just say hypothetically that n was equal to 5, right? So good thing we didn't just say n was the even number because 5 is definitely not even, but because we said the first even integer would be 2n, then this would be equal to 10 because 5 times 2 is 10, and that's definitely an even integer. That being said, if this is 2n plus 2, all even numbers are 2 away from each other, right? So 2 times 5 is 10 plus 2 would be 12. This would equal 12, which is the next consecutive even integer. Or looking at this one, this expression also works for that second even integer. It just happens to be smaller because 2 times 5 is 10 and 10 minus 2 would be 8. So is 8 also consecutive to 10? Sure it is, it's just in the other direction. So either of these second expressions for the second even integer are fine. One of them just tells you the larger integer, while the other one would tell you the smaller integer instead. For good measure, if you wanted to try this again with another random number, like n is equal to, I don't know, something like 12. If we said n was 12, then the first even integer here would be 24, because 2 times 12 is 24. Over here, 2 times 12 is 24 plus 2. That means this one would be 26, which would be the larger even integer. And if we did it over here, 2 times 12 is 24 minus 2, which is 22, which would be the smaller integer if we were comparing it to 24. So these expressions would give us our two even integers that are consecutive. Now, between these two expressions over here, it's up to you which one you want to use, as long as you know which one would give you the larger or the smaller integer. But for me, in this practice problem, I'm going to use this 2n plus 2 as my second even integer, which is going to be the larger one. And I'm going to go ahead and use this 2n to represent the value of the smaller even integer. Alrighty, so let's go back to the problem. We are told that the square of the smaller integer is going to be 10 more than the larger integer. So we should be able to take that smaller integer, which we know is going to be 2n, and we can supposedly square it. So we'll go ahead and raise that to the second power, and that's going to be equal to 10 more than the larger integer. So the larger integer we just said was going to be that 2n plus 2, and it's supposed to be equal to 10 more than that when we square the smaller integer. Alrighty, cool. So now we have a quadratic equation, but it's kind of difficult to solve right now. So let's see if we can clean this up a little bit. On the left side, 2n squared, that's 2n times 2n. Be careful with that. So 2 times 2 is going to be 4, and then n times n is going to be n squared. On the right side, let's go ahead and just drop those parentheses because they're not necessary. They don't change anything if we get rid of them. So we have 2n plus 2 plus 10. Then we can go ahead and combine some like terms on the right side. We have those constants of 2 and 10, so let's have 4n squared is equal to 2n plus 12. Next, let's go ahead and put this into standard form by setting this whole thing equal to 0. So on the right side, let's go ahead and take away 2n and take away 12 at the same time, and I'm going to go ahead and do that on the left side as well. If you want to split this into 2 steps, that's fine too. I'm just being a little bit lazy here. Subtracting that 2n and 12 from both sides, we're going to have this rearranged equation of 4n squared minus 2n minus 12 is equal to 0. At this point, you can go ahead and see if you can solve by square roots or factoring or completing the square or the quadratic formula. It's your choice. I'm going to go ahead and try factoring here. I don't think we can solve by square roots. So I'm going to write 4n and 1n. That would get you that 4n squared. And then for the negative 12, maybe I'll try something like negative 6 and a positive 2. Let's see if this works here. If I go across, that's negative 24n plus 2n, that's negative 22n, that's not what we want. But if I go diagonal, this is going to be 8n minus 6n, that's going to get us positive 2n. So here's what we can do. We just want a negative 2n, right? So let's go ahead and switch these, and I'll make this one the negative 2 and make this a positive 6. So if we go ahead and multiply diagonally, this would be negative 8n plus 6n, which would be negative 2n. Okay, so looks like we can factor, which is nice. We can avoid using the quadratic formula. I'm going to go ahead and open up my binomials and set them equal to 0. Okay, so it looks like the 4n was paired with the minus 2, so I'm going to make those my outers. And then the positive n and the positive 6 were paired, so those will be our inners. If you want to pause the video to see if that makes sense and FOIL it out, you can double check to make sure that works. But I think now that we have our linear binomials, we can go ahead and solve for n. So let's see, if we can make this linear binomial equal 0, that would be one of our solutions. So 4n plus 6, let's just set it equal to 0. If we take away 6 from both sides, we would get 4n is equal to negative 6. And if we divide both sides by 4, we're going to find n is equal to negative 6 over 4, or negative 3 over 2. So that's one of our solutions, but for our other one, that's a little bit easier. If we set n minus 2 equal to 0 and add 2 to both sides, n would equal positive 2. So these would be our two solutions for the value of n. All right, so now let's think back to our original expressions. We had this 2n for the smaller integer, and we also had this 2n plus 2 for the larger integer, but we have two possibilities for values of n. Let's see what's going on first when n is equal to this negative 3 over 2. So let's see here, if we say that n is equal to this negative 3 over 2, let's go ahead and see if we plug that into each of these expressions and see what our first even integer and second even integer are going to be. So taking this negative 3 over 2 and substituting into this first expression, 2 times negative 3 over 2 is just going to equal negative 3. So that's going to be that first even integer based on what we just got there. And then if we go ahead and take this negative 3 over 2 and substitute it into this expression, 2 times negative 3 over 2 is just going to be negative 3. Negative 3 plus 2 is going to equal negative 1. So these would be the two numbers that we would get here. And notice how this doesn't really make sense, because after all, we are looking for even integers, and these over here are odd integers. So while they are consecutive and they may algebraically work, that is not what we were looking for. If you want to see if this algebraically works out, we said earlier that the square of the smaller number, which is negative 3, if we square that, it was supposed to equal the larger number, it's supposed to equal 10 more than that. So if we square the negative 3, we do get this positive 9, and then negative 1 plus 10 does equal 9. So while algebraically does check out, these are not even integers. What about possibility number 2, where n was equal to 2? So let's check that out and see how that works out for us. For our first even integer, if we take this 2 and substitute it into this 2n, 2 times 2 is going to be 4, so that would be the first even integer, and that's actually even, so that's good. And then if we take this 2 and substitute it in here, 2 times 2 is 4, plus 2 is going to be 6, so the second even integer would be 6, and that is indeed another even integer. If we want to check this, we can see if we square the smaller one, take that 4 and we square it, it should be equal to 10 more than the bigger one. So if we take that 6 and we add 10, 4 squared is 16, so 16 does equal 16. So both of these algebraically check out, but we can see that when we're looking for two consecutive even integers, these are two even integers, and they are actually positive, which is what we're looking for. In conclusion, we found out that these two numbers that we're looking for are 4 and 6. So there you have an application word problem where we had to set up a quadratic equation to look for some missing integers. If you found the video helpful, please consider giving it a thumbs up and letting me know in the comment section down below. You can also share this video with a classmate or friend who might also find it helpful. And as always, keep up the great work that you're already doing, and I'll see you in the next one.